Alright, so this is part 2 of our topic 2.3 series, looking at carbohydrates and lipids. If you haven't already watched part 1 about carbohydrates, go ahead and do that now. In this part, we'll be talking about lipids and discussing the biochemistry that we need to understand. So what are lipids? Lipids refer to fatty, waxy, or oily compounds. So when I think lipids, I just think fats and oils. It's a very simple way to remember what lipids are. And many types of lipids, such as triglycerides, which are a type of lipid, and phospholipids, which are another type of lipid, are made up of or composed of fatty acid chains. So before we really go into understanding lipids, we need to look at fatty acid chains. So triglycerides refer to compounds where we have a glycerol head, so that's where that glyceride part comes from, and then the tri means that we have 3 fatty acids. So triglycerides are a glycerol head and 3 fatty acid tails or chains, and then phospholipids are a modified triglyceride. Instead of having 3 fatty acid tails, they have 2 fatty acid tails, and instead of a glycerol head, they have a phosphate head. So fatty acids can be saturated, monounsaturated, or polyunsaturated. So before we delve into looking at what that means, we first need to understand that fatty acids are hydrocarbon tails. Now, while they are made up of carbon and hydrogen, we can also sometimes get double bonds between our carbons. So depending on the number of double bonds between our carbons, we can classify fatty acids as either saturated, monounsaturated, or polyunsaturated. Let's have a look at this in more detail. Saturated fatty acids have no double bonds between carbons. And because of this, there is a maximum number of hydrogen atoms that can be packed onto that carbon. So one thing to note is that carbon can form 4 bonds. And so where we have single bonds between our carbons, we can fit in more hydrogens onto that carbon. Let's have a look at this. So this is a saturated fatty acid. If we pick any random carbon from here, we can see that it is single bonded to adjacent carbons. So because carbon can form 4 bonds, and there's a single bond between carbons, that leaves room to pack on 2 hydrogens onto every carbon. Contrast this with unsaturated fatty acids, which do have double bonds between carbons. This means that less hydrogen atoms can be fit onto the molecule. So if we have a look here at this unsaturated fatty acid, there is a double bond between these carbons here. And because once again, carbon can form 4 bonds, that means we've got 2 bonds here. We've got 1 bond going on here, which leaves only 1 bond left for hydrogen. So we can only fit 1 hydrogen onto this carbon and 1 hydrogen onto this carbon. Whereas if we contrast that here, we could fit 2 hydrogens onto every carbon. So that's why we refer to this as saturated, because it's saturated with hydrogens, whereas we refer to this as unsaturated, because it doesn't have a full degree of saturation of hydrogens due to the presence of that double bond. Now we can look at unsaturated fatty acids by breaking them down into monounsaturated fatty acids, where there's only 1 double bond between carbons. And then we also have polyunsaturated fatty acids where there are more than 1 double bonds. So this example here would be a monounsaturated fatty acid, so 1 double bond, and we see that double bond here. If there was more than 1 double bond, then this would be a polyunsaturated fatty acid. Now the presence of double bonds causes a kink in the shape of the molecule, and as a result, unsaturated fatty acids are bent in structure. Because unsaturated fatty acids are bent in structure, this means that they cannot be nicely packed to make a solid. We know that solids refer to substances where the molecules are nicely and tightly packed together, which gives it its solid shape, whereas liquids, the molecules are loosely bound, and that's why it is able to move in this liquidy sort of manner. So for this reason, unsaturated fatty acids tend to be liquids at room temperature, because the bend in their molecule doesn't allow them to be nicely packed together to make a solid. If we contrast this with saturated fatty acids, because they are straight, there is no bend in their shape, saturated fatty acids can be nicely bound and packed together to form a solid. Hence, saturated fatty acids are solid at room temperature, whereas unsaturated fatty acids tend to be liquid at room temperature. Now, in our last video, we learned how to draw glucose, and another thing that we need to learn how to draw is a saturated fatty acid. So a fatty acid in which there are no double bonds between our carbons, and it is a very straightforward process. We start by drawing a carboxyl, and if you are a chemistry student, you know that this refers to where we have a carbon that is double bonded to an oxygen and single bonded to a hydroxyl or to a OH. So we start by drawing our carboxyl when we want to draw a fatty acid. Then we add in our hydrocarbons. So a hydrocarbon, once again, just refers to carbons and hydrogens. So we fill in our carbons and then we make sure that we put in our hydrogens. Now, because this is an unsaturated fatty acid, all our bonds between our carbons are single. Another thing to note is that when we finish off our fatty acid, the last carbon has 3 hydrogens on it compared to the other carbons where they have 2 hydrogens. And the reason for that, once again, is that carbon forms 4 bonds. So with our final carbon, when we want to terminate the molecule, we need to make sure that there are 4 bonds present. Otherwise, it doesn't make sense as a molecule. And for that reason, we put in our 2 hydrogens on top and below, but we also put in a hydrogen at the end to give it the 4 bonds it needs. The last thing to note is that in past exams, people have lost marks for not making their hydrocarbon tails long enough. And usually the rule of thumb is to make sure that there are at least 4 carbons in your hydrocarbon tail. So here we can see that we've got 1, 2, 3, 4 carbons in our hydrocarbon of the fatty acid. So you need to make sure you draw in at least 4 carbons in the hydrocarbon aspect of your fatty acid to get the full marks. For safety's sake, I would say draw more. So if you can draw 6, 8, do so. So usually if you're asked to draw a fatty acid, you need to include your carboxyl. You need to make sure there are at least 4 carbons in the hydrocarbon part of your fatty acid, and you need to finish off your fatty acid with 3 hydrogens on that terminal carbon. That's it, very straightforward. Now let's have a look at unsaturated fatty acids in a bit more detail. What we need to understand is that unsaturated fatty acids can be cis or trans isomers. So they can exist as either a cis unsaturated fatty acid or a trans unsaturated fatty acid. What does this mean? Cis unsaturated fatty acids refer to where we have hydrogen atoms attached to the carbon double bond on the same side. So if we have a look at an image, this here is a cis double bond. And if we zoom in, you can see that this is an unsaturated molecule because of this double bond, and we refer to this as a cis unsaturated molecule because the hydrogens associated with that double bond are on the same side. Compare this to a trans unsaturated fatty acid. So it is still unsaturated because we have this double bond here, but the hydrogens associated with the double bond are on opposite sides. So we have one below and one on top. So cis means same. Trans, you can think of transitional, so going from one side to another. And so with trans, our hydrogens are on the opposite side, whereas with cis, they are on the same side. Now remember, these are still both unsaturated fatty acids. One is cis, one is trans. Now, cis fatty acids tend to be naturally occurring, whereas trans fatty acids are typically produced in industrial processes, and this process is referred to as hydrogenation. Now, hydrogenation is usually done to make oils such as vegetable oil and olive oil, which we know will usually be liquid at room temperature, into semi-solid spreadable butters. So by the process of hydrogenation, we can turn something like olive oil into a semi-solid spreadable butter. So if you've ever seen olive oil butter or olive oil spread, this was achieved through the process of hydrogenation. So now we need to understand some scientific evidence behind the health risks of trans fats and saturated fatty acids. So some lipids are associated with increased health risks, particularly trans unsaturated fats and also saturated fats. Saturated fats and trans unsaturated fats increase what is referred to as LDL cholesterol. or sometimes you might hear it referred to as bad cholesterol. So saturated fats and trans unsaturated fats increase quote unquote bad cholesterol in the bloodstream. Some examples of sources of saturated fats include animal products like beef and butter, and some sources of trans unsaturated fats include processed snack foods and fast foods, deep fried foods, etc. Cis unsaturated fats lower bad cholesterol. So examples of sources of cis unsaturated fats are almonds, vegetables, fish, and olive oil. Now, we need to understand a little bit more about what we call quote-unquote good and bad cholesterol. So not all cholesterol is bad. We actually need cholesterol, particularly in the formation of our cell membranes. However, the health status of cholesterol depends on what it is associated with. So cholesterol travels with these compounds called lipoproteins. So you can imagine cholesterol hitches a ride on lipoproteins, and then depending on the type of lipoprotein that the cholesterol is hitching a ride on, that is going to determine the status of cholesterol, whether it is good cholesterol or bad cholesterol. So cholesterol that travels with low density lipoproteins is referred to as bad cholesterol because it raises blood cholesterol levels. Whereas cholesterol that hitches a ride on or is associated with high density lipoprotein is referred to as good cholesterol because high density lipoproteins actually look for excess cholesterol and take it to the liver to be disposed of. So our high density lipoproteins will scavenge for any excess cholesterol in the blood and take it to the liver to be destroyed. And so as a result, we call high density lipoprotein cholesterols the good cholesterols. So what cis unsaturated fats will do is they increase our good cholesterol. Compare this to saturated fatty acids, which increase our bad cholesterol. So this is why saturated fatty acids have associated health risks. Now the big gun are the trans unsaturated fatty acids, because not only do they increase bad cholesterol, but they also decrease good cholesterol. So while saturated fatty acids do increase bad cholesterol, our trans unsaturated fatty acids do that and also decrease good cholesterol. And so remember, our cis unsaturated fatty acids refer to where there's a double bond between our carbons and the hydrogens are on the same side. Compare this to saturated fatty acids where there are no double bonds between carbons, and then trans unsaturated fatty acids where there is a double bond between the carbons. So that might make you think, oh, this is one of the good guys. However, this is made from industrial processes, and we know that the hydrogens associated with that double bond are on different sides. And so our body is not used to seeing this kind of configuration and doesn't know how to deal with this. And so trans fats can have some really adverse health risks. Now, why is high cholesterol so bad? We've talked about how certain lipids can increase bad cholesterol, decrease good cholesterol. Why does this matter? So cholesterol can build up in the bloodstream and then harden on the blood vessels, so harden in our arteries and veins, and this leads to a narrowing of the arteries. This narrowing of arteries is referred to as atherosclerosis, and when we have a narrowing of arteries or where we have atherosclerosis, blood flow can become restricted. Now, if our coronary arteries become blocked, this can lead to a stroke. So coronary arteries are really important arteries because we know everything in our body needs a blood supply, and that includes our heart. So coronary arteries are these special arteries that actually supply the heart itself. And so if the heart stops receiving its own blood supply and its own nourishment, then it will not be able to carry out its function of pumping blood to other parts of our body. And so blockage of coronary arteries is really, really serious and can lead to stroke. So here is a table from BioNinja and it gives some sources and examples of the different types of fatty acids and labels them as either good or bad. However, I would like to note that while it is nice to have some sort of biochemical understanding regarding what we refer to as good and bad fats, it is important to be mindful that we should never assign moral value to food. So just do everything in moderation and give your body the fuel it deserves. Don't get too caught up in labels unless, of course, you have to write an exam, in which, yes, this is quite important. But when it comes to daily living, yes, be mindful of food choices, but do not assign moral value to food. Now let's quickly have a look at some different functions of lipids. Lipids are actually quite important in the body. Even though they do get a bad rep, fats and oils, they do have some important functions in our body. One function of lipids is, we've talked about how it can help with transporting cholesterol around the body. So lipids are very important in the formation and transportation of cholesterol. Another function of fats particularly is in insulating and protecting our organs. So it's nice to have some what we call visceral fat, or fat around our organs, obviously not too much, but enough to insulate and protect our organs. Lipids are also involved in chemical messaging, so lipids can attach to the surface of different cells and mark them, for example, marking them for destruction. Lipids are also important when we talk about dissolving and transporting fat-soluble vitamins around our body. So examples of this would be vitamin A and vitamin D. These vitamins are not soluble in water, so we need to have a relatively good lipid content in our body, or fat content in our body, so that these fat-soluble vitamins can also be used. A very important function of lipids is in cell membrane formation. So earlier we talked about phospholipids as being a phosphate head with two fatty acids attached to it, and so we can see here how these phospholipids are really important because we know that phospholipids make up our cell membrane. So we've heard of the term phospholipid bilayer, which is what our cell membrane is made of, and so we can see here how lipids are really, really important. And another really important function of lipids is for storing energy. So we can store energy as triglycerides, which are a glycerol head with 3 fatty acid chains, and sometimes we can store energy as triglycerides. Now we need to understand how triglycerides are formed. So we talked about how it is 3 fatty acids combined with 1 glycerol, and this combination, or this reaction of the fatty acids to that glycerol head, is done so by a condensation reaction. Now you should be able to tell me what a condensation reaction is. So if we have a look here at this triglyceride, this here is our glycerol head. So this is what glycerol looks like. And this is 1 fatty acid chain, this is the 2nd fatty acid chain, and this is the 3rd fatty acid chain. Now, because this is a condensation reaction, we know water is going to be formed, and how this takes place is that a H of our glycerol reacts to an OH of our fatty acid and forms a water molecule, and because we have 3 of these, we're going to have 3 water molecules formed. When this happens, we then see a link taking place between our carbon from our glycerol and our carbon from our fatty acid, with oxygen forming that bridge. So if we have a look here, we've got a carbon to oxygen to carbon bond. So this here is a glycerol head bonded with one of the fatty acid chains. The glycerol head, same glycerol head, is bonded with another of the fatty acid chains, and then once again that same glycerol head, just a different part of it, bonded with a 3rd fatty acid chain. And so this here is our triglyceride. So it is a condensation reaction because water is produced. Now, one thing we need to do is compare carbohydrates and lipids. So one of the understandings that comes from your syllabus is that lipids are more suitable for long-term energy storage in humans than carbohydrates are. So in the previous slide, we talked about one of the functions of lipids being energy storage, usually as triglycerides. However, if we remember back to the last video, we also talked about glycogen being a form of energy storage in animals. And so if they're both energy storage methods, we need to be able to compare and contrast them. So while lipids and carbohydrates can both function as energy storage molecules, they have different characteristics. So the acronym that I like to use to remember this is SADS. So the S in SADS stands for storage. And so when it comes to storage, lipids are more suitable for long-term energy storage compared to glycogen. So glycogen is more of a mid-term energy storage, whereas lipids are long-term. So, for example, let's say you're fasting or you're in a desert or something, and for some reason you don't have food supply. The first thing your body will do is use up all the glucose that it can find. The next thing it will do once it runs out of glucose is that it will go to glycogen stores. So it'll access the glycogen and make energy from the glycogen. If you for some reason have a prolonged period of time without food, then your body will start to burn up the fats and the lipids that it can find. So lipids are more suitable for long-term energy storage. They're the last resort when it comes to making energy. The A in SADS stands for ATP yield. So lipids actually store more energy per gram than carbohydrates. And this may lead you to wonder, okay, if lipids can give us more energy when we metabolize them, why don't we use them first before glucose and glycogen? Well, this is because of the next 2 points. Carbohydrates are easier to digest and use than lipids. So that's the reason why lipids are used for long-term energy storage, whereas glucose, even though it gives a lower ATP yield, is used first because glucose is easier to digest and to use. The last point is solubility. So carbohydrates are also easier to transport in the bloodstream, and that is another contributing factor as to why it is used before lipids. So we know that oils and fats do not really dissolve well in water, and so for this reason, lipids are less soluble in the bloodstream, whereas carbohydrates are easier to transport in the bloodstream. So just remember SADs, think about storage, ATP yield, digestion, and solubility when comparing carbohydrates and lipids. Now, the last thing we need to be able to do is calculate BMI. So from your IB syllabus, it is stated that you need to be able to determine body mass index by either calculation or use of a nomogram. So firstly, BMI is a screening tool that is used to identify potential health risks in adults. So we know that there are some associated issues with increased BMI, such as risk of stroke, heart attack, diabetes, etc. So what it does is it measures weight in relation to height. So getting someone's weight alone is not necessarily an accurate measure of their health, because we know if someone, for example, is really tall, they're going to have a greater weight than someone who is small. And so it is important to have a measure of weight that is in relation to height, so that takes height into consideration. And so that's what BMI does. And it can be calculated with the following formula. It's quite simple. You get the mass in kilograms and you divide this by the person's height in meters squared. And so it's a very simple formula. Another way in which we can determine BMI is using a chart called a nomogram. And so this is what it looks like. And so on this x-axis here, we have height in meters, and then down the y-axis, we have their weight in kilograms. And so if you find the two and the point in which they meet, then you can determine BMI. So for example, if you're 1.60 meters tall and you weigh 70 kilos, you go down until you find the 70 kilo mark. So this is 70 kilos, this is the 1.6. Where they meet up is here, and so the BMI here is 27.1. And so there is also a color code to determine what this BMI means. So whether someone is the normal weight, whether they are underweight, whether they're overweight, or whether they're obese. And different nomograms will look slightly different. So sometimes instead of having a color-coded key, they'll actually have these descriptors somewhere on the nomogram. But either way, you can use this to determine somebody's BMI and the category that they fall into. And we'll have a look at this in a following slide. Now, while BMI can be a nice screening tool, it is not a diagnostic tool. So for example, you cannot diagnose someone straight away with diabetes just because they have a high BMI. However, a high BMI can then trigger you into doing further investigations into whether someone may have these potential health issues, and can be a really good starting point. While BMI is a nice measure or screening tool to have, there also are some limitations. So obviously, in pregnant women, BMI values are not a valid indicator. But also, if we think about athletes and people who do, for example, maybe heavy weightlifting and muscle bulking, they have very atypical muscle to fat ratios. So their BMI might come up as high. However, it is not actually because of fat. It is due to muscle. And so it would be sort of incorrect to say that such a person is at risk for something like diabetes, because we know that their high BMI is not as a result of a high fat content, but because of their muscle content. So this is where BMI can sometimes fall through. So that's it. But before we finish off, let's do a couple of practice questions. So these questions relates to both this video and the video that was previously uploaded on carbohydrates. And so once again, if you haven't watched that, I do recommend you go ahead and do so. So pause the video before I give the answer away and have an attempt at answering the following questions. Which molecule is a polysaccharide? A, glucagon, B, glucose, C, glycerol, D, glycogen. Pause the video here before the answer is revealed. So the correct answer is D, glycogen. So glycogen here is a polysaccharide. If we compare this to maybe glucose, glucose is a monosaccharide. So if you picked B, that's why that would not be the correct answer. Glucagon we haven't quite learnt about yet, but this is a hormone involved in regulating blood sugar levels. And today we talked about glycerol, and we definitely know that glycerol is not a polysaccharide. Next question. Which substance is used for structure in plants? A, amylopectin, B, cellulose, C, collagen, or D, starch? Pause this video before the answer is revealed. So the correct answer is B, cellulose. So we know that cellulose is used in structure for plants, and it's found in their cell walls and helps give the cell wall that rigid geometrical structure. We've heard of amylopectin and starch. So amylopectin is a type of starch, the other type of starch being amylose, and we know that starch is a form of energy storage in plants. So while cellulose is used for structure in plants, starch, namely amylose and amylopectin, are used for energy in plants. The next question is a little bit of a tricky one because we haven't necessarily covered everything revolved around this question. However, you should be able to get at least 50%. Pause this video if you need some time. So you should have been able to get A and D. A is a carbohydrate, specifically it is a monosaccharide, and we can see that by its simple ring structure. And D here would be a lipid. This is a saturated fatty acid. We can see the carboxyl here and the hydrocarbon part here, and it's saturated because all the bonds between our carbons are single bonds. B and C were a bit more tricky. So B is actually also a lipid, and this is actually cholesterol. So we've spoken a little bit about cholesterol today, but I didn't show you a molecular diagram of it. So this is actually what it looks like. So it's 4 fused rings, and then it has these little bits coming off it, which you don't necessarily need to memorize, but cholesterol is known for its 4 fused rings, and cholesterol is a type of lipid. And then C, this would be an amino acid. So we haven't yet discussed amino acids, but just to introduce you to what they look like, this is their general formula. So amino acids are characterized by this NCC backbone, and then we have a carboxyl on one side and then the amine group on the other side, hence the name amino acid. But more about that in a video to come. The next question is a short answer question and asks you to draw the structure of a saturated fatty acid. Pause the video if you need. So the mark scheme describes that to get the full 2 marks, you need to have a hydrocarbon chain with single bonds and at least 4 carbons. So if you drew any double bonds between the carbons, that would be wrong. And if you drew less than 4 carbons, then that would also be wrong. So you would not be able to get that mark. However, if you did both of those things, then that would be 1 mark. And then the second mark is awarded if you have a carboxyl at the front. So this C double bonded to an O, single bonded to a hydroxyl, and then 3 hydrogens on the other end. So if you have both of those things, that will get you the second mark. If you only have 1 or none of those things, then you don't get that second mark at all. Now this comes from a previous paper, and so this was the mark scheme that was actually used for that paper, and it was quite brutal. So in order to get those 2 marks, you need to make sure you meet all these criteria. Now, the final question requires you to look at this nomogram and state the lower weight limit for a woman with a height of 155 centimeters who is classified as overweight, giving the units. So that's the lower weight limit. Pause this video if you need. The second part of the question asks you to state a major health problem of the circulatory system that is correlated with obesity. Pause this video if you need. So the lower weight limit would be 60 kilograms, and so this is because we know with the information given that the person is 155 centimeters, so we look for that height here along the x-axis, and we can see that's here. And then we know that they are classified as overweight, which means if we come up, they should be somewhere in this gray area. Now we're asked to find the lower weight class or the lower weight limit. And so the lower weight limit for someone who is 155 centimeters and overweight, the lower weight limit for being overweight is 60 kilograms. And so that's the answer. Now, in order to get the point, you need to make sure that you include that unit of kilograms. In terms of a major health problem of the circulatory system related to obesity, some of the ones we discussed today are coronary heart disease, stroke, and atherosclerosis, but any of these options here, if you wrote them down, would be considered worthy of gaining the mark. So make sure you're able to relate back to these sort of issues of coronary heart disease, stroke, and atherosclerosis, rather than just the theory of lipids. That's it for today's video. Happy studying.